Hello and welcome to episode 14 of the Minimapper series. Today we're going to start talking about communications. But before I do that, I want to say something about the status of this motor prototype board. Let me see if I can show you this. I'm going to need to put a bit of paper up in front to trick the autofocus on this camera. But I've got the boards made by Eisler and they look very nice. I also got some of these made, and these are oh, come on, focus. These are motor encoder discs they're just made as bits of PCB. So come on, there we go. I drew this the shape up in FreeCAD and then imported it into KiCad and made a little PCB design from these things. And with a bit of help from the people at Eisler, I was able to get those manufactured. And so I'm going to use those for the motor encoder, and they look pretty good. So I've got the boards and I've got the parts. I could go ahead and put these things together and start doing experiments with them. But I'm working on some software to go with this stuff. I'm going to connect the motor prototype board to an STM32 Nucleo development board for doing experiments. And I've started writing some software for that. And it's taking a little bit longer than I thought it would, as these things usually do. But I'll come back to this once I've got the software in a state where I'm ready to get going with it. But in the meantime, we can talk about the next thing. We can start talking about the next thing, which is, I don't know if you remember, you probably don't remember, but one of the second sub-project for the Minimapper that I want to do is some means of communication between the Minimapper robot and PC. And that's what this is about. I'm calling this thing Link-434. So I didn't want to use Bluetooth, didn't want to use normal Wi-Fi, so I'm going to use the ISM 434 megahertz band, hence Link-434. And so we can just get into it. As normal with these things, the first thing I want to do is talk a little bit about some requirements for this. So let's do that. So the first thing is this, what I'm calling USB dongle form factor. And what I mean by this is, I've got another thing I can show you. So this is a piece of paper again, autofocus, come on. So this is a little thing made by Nordic Semiconductor, and it's a little dongle or little board that you can connect to the USB port on your PC, and it has one of the nRF52840 microcontrollers on it, and this thing has a 2.4 gigahertz radio, so you can do Bluetooth and OpenThread and Zigbee and things like that. And it's a nice little form factor. If you can hear the clicking in the background, that's my dog coming in and looking around. It's a nice little form factor, and it's very convenient because you plug this thing into your PC. It has a USB bootloader on it, and so you can program it from the PC very easily, and you can do all kinds of Bluetooth and other 2.4 gigahertz radio experiments with it. And so I like that form factor, and that's what I want to do for this thing. The second thing is that although doing things with USB is very convenient, when you're working on a PC, it would be really useful to have an easier way to connect this to the Minimapper, because I really only want to make one radio thing, and so what I want is a little board that I can plug into the PC through the USB port, but I can also attach to the Minimapper through a UART. And so I don't know if you'll be able to see this, but I'll show you on this this Nordic board again. So it's not too bad. So along the edge of this thing, there are these castellated holes. So these are half holes that are plated, and you can solder 0.1 inch headers to them and then attach this little Nordic board to another board. And so I want to do the same, but probably not with castellated holes because I don't quite know how to do them properly in KiCad, and I don't know if Eisler can make them cheaply. But just some holes to put 0.1 inch headers in, and then the Minimapper board can have one of these things riding on top of it and talk to it through a UART. The next thing is about networking protocols. And so one of the main reasons I didn't want to use Bluetooth or Wi-Fi or any of those standard things is just because the protocols are quite complicated, and the software side of things is often very complicated. So what I'm going to do is build a very simple set of network protocols from the bottom up, and implement those. And that should be educational, and for this simple case, it should be enough. So another thing that I've been inspired by some of the Nordic stuff is this idea of a tunneling daemon. So if you do stuff with OpenThread, which is one of the network protocols supported by the NRF 52840, there's this thing called WPAN-TUND, which stands for Wireless Personal Area Network Tunneling Daemon. And this is a user space process that you can run on Linux, and it talks to the NRF 52840 dongle over the USB port using a protocol. The protocol doesn't matter. And the WPAN-TUND thing allows the USB dongle to look just like a normal Linux network interface. So this gives you access into the OpenThread mesh network via all your normal Linux networking tools. And now the protocol that these things talk is complicated because OpenThread presents a whole IPv6 network, mesh network, to the devices on it, and you can imagine that's quite complicated. There's also stuff to do with mesh maintenance and routing and all the IPv6 stuff as well. So the protocol that the WPAN-TUND talks to this dongle is very complicated. It's a thing called Spinal. In my case, it should be much simpler, and so I'm going to try and write a thing that will probably be called Link-434 TUND, Link-434 tunneling daemon, to do the same kind of thing, to present this as a Linux network interface. So the last thing on this list is this idea of a suitable level of integration for learning. And so you can buy completely integrated boards for 434 megahertz communication from Adafruit, and I'll put a picture of one in here. So there's something you can buy from Adafruit that does this. I don't want to just buy a board from Adafruit. I'm going to learn how to do this myself. And this idea of a suitable level of integration goes not just to this thing where you wouldn't buy a single board to do it, but you can get devices that are very highly integrated, as we'll see when we look at transceivers in a minute. And I want to choose something, or choose an approach that allows me to break open some of the black boxes that there are in these things and understand how some of the things inside work. And now, talking about learning, I just want to say something about learning objectives for this sub-project, because there are a few. So first of all, I want to learn a little bit about USB and a little bit about RF. And so when I say a little bit, I really do mean a little bit of these things. In terms of USB, last week or the week before last, I read Jan Axelson's book, USB Complete. Boy, it's complicated, and it's not complicated in a very interesting way either. It's a protocol that's developed through various versions, and it's intended for so many different applications that it's got lots of bits to it, and it's not an enjoyable thing to learn about. So from my perspective, all I want to be able to do is set up a microcontroller to present a virtual serial port over the USB so I can connect it from a PC. If I can get that working, I'll be happy. That's enough USB for me for now. RF is also complicated, but it's complicated in a very interesting way, and I would like to learn more about that stuff, but I want to take it step by step. So I believe for this project, the only bit of RF layer I need to do is a transmission line going from the transceiver to an antenna. And there might be some stuff to do with antenna matching networks and things, but I'll copy that from an application note or an evaluation board. I might try and do some more detailed study of transmission lines, because there are some open source EM modeling tools out there now, like OpenEMS and Elmer and some other things. And I might have a go at doing some things with those, just for amusement value. So one part of the whole RF side of things I do want to learn more about is modulation and demodulation. And this application uses kind of the simplest form of modulation that there is, called on-off keying. And basically it means that if you're transmitting a logic level 1, you're transmitting some RF power. If you're transmitting a logic level 0, you have your transmitter switched off. And sometimes it's called AS key for amplitude shift keying. And some transmitters you can't switch them all the way off, so you just have a high power level and a low power level. But this is much simpler than the kind of complicated frequency shift keying or phase shift keying schemes that are used for Wi-Fi and Bluetooth and things like that. So it's a good platform for learning about some of these things. And so I want to try and implement as much of the modulation and demodulation process myself in software as I can. And that has some implications for the devices that I choose to use. Next, I already talked about the complications of the network stack for Bluetooth and Wi-Fi, and so I'm going to build a DIY network stack, which will be simple. So, for instance, like I said, OpenThread has all this stuff to do with mesh maintenance and IPv6 addressing and stuff like that, and I won't need any of that. I'm going to have 2 devices, maybe 3, so they'll just need an address. Depending on the transceiver, it might be possible to switch between different channels, and there'll be something to send data back and forth, some framing, some checksums for error detection. Nothing very clever or complicated. So it should be relatively straightforward to do this. The other thing is to learn another microcontroller. So I've been doing lots of stuff for the microprototype board with the STM32, and the Minimapper board, the main Minimapper board, will eventually have an STM32 on it. And there's a problem when you do lots of work with one processor or one programming language or whatever, which is that you get really into it, and you end up thinking that the way that this microcontroller or this programming language does things is the only way to do things. So with a microcontroller, the way that interrupts are handled, the way that DMA works, the way that you set up a GPIO, the memory map, the processor instruction set, you can easily end up thinking that that's the way things are. But it doesn't have to be that way. And it's the same with programming languages. If the only programming language you've seen is C, then you have a particular view of how computers work and how programming works. If the only programming language you've ever seen is COBOL, you have a different view of the world. But if you've learned C and C++ and Lisp and Haskell and Perl and Python and whatever else, then you get a much broader view. And what it helps you to do is to work out what things are fundamental and what things are contingent on a particular programming language, or in this case, a particular microcontroller architecture. So I'd quite like to use a different kind of microcontroller for this. And I'll talk about some options a bit later. So based on the requirements, this thing is actually pretty simple. It's got a microcontroller, which will do all the protocol handling and stuff like that. And it's got a transceiver that'll send stuff over an antenna. Now, there's a few lies on this picture, but I'll talk to it. It's a cartoonish kind of schematic view of how this might look. So the microcontroller has a USB connection and another connector that goes through UART. So it can either talk to the USB or talk to the UART, and it'll detect whether the USB is there when it starts up. If the USB is there, it'll talk over USB, otherwise it'll talk over the UART. Simple. There's some indicator LEDs and a switch. People say you should never build any kind of embedded thing without an LED on it, and who am I to argue with that? And then you've got the transceiver, and I've based what there is here on the device that I'm tending towards using. And so this thing has an I2C bus for setting up configuration stuff, but the interface for transmitting data is really simple. So there's a pin to enable the transceiver. There's a pin to switch between transmit and receive mode. Logic high is transmit, logic low is receive. And then there's a bidirectional data pin. And so if you want to transmit something, the microcontroller just wiggles this pin in the pattern of bits it wants to send, and the transceiver wiggles the output to the antenna to send that bit pattern. And similarly, when you're receiving, the transceiver wiggles this line in the bit pattern of the data it receives. So that interface is really simple. And then on the microcontroller side, you need I2C connections for the configuration. And then these other connections will just be GPIOs. So this one's an output switching the transmit receive mode. This one's an output enabling the transceiver. And this one will have to switch between input and output because use it as an output for transmit and an input for receive. And there'll be some timer type stuff to do with synchronizing the receive clock on this. I'll talk about that in a minute. One thing that is very cartoonish here is this connection to the antenna. This turns out to be a bit more complicated because you're using the antenna for send and receive, and most of these transceivers have some kind of matching network out here and some multiple connections for the antenna. But that stuff I can copy from an application note. I've not decided what kind of antenna to use here. This Nordic Dongle uses a little PCB antenna, but because it's using 2.4 gigahertz, that's quite small. At 434 megahertz, PCB antenna ends up being quite big. I think I can't remember, the wavelength is something like 17 centimeters, or maybe the quarter wavelength is 17 centimeters. So it ends up being inconveniently large anyway. And so the options here are something like a whip antenna. So that's a thing with a little SMA connector on the bottom and a wire going up it with a coil in it. And then it's got a little plastic cover over it. The kind of thing that you use to extend the range of your Wi-Fi router. And the other option is just a piece of wire, because the range that this thing needs to transmit over is very short, and having a well-matched antenna might not really matter very much. So, I mean, that's basically all there is to it. And so if we think about parts that we might choose, on the transceiver side, there's a range of options in terms of level of integration. And this is like the most integrated part you can get. This is made by Analog. This has a microcontroller in it. So everything on this side is microcontroller stuff. Everything on this side is the transceiver. I'll talk about what's in the transceiver side in a minute, because they're all more or less the same, and there's a better picture from one of the other parts I'll show you in a second. But this kind of super integrated version of things, it'd be very useful for product development, because you just need one part and you've got a fairly powerful microcontroller and you've got your transceiver. But for what I'm doing, I want something less integrated than this. This is what I said about breaking open these black boxes. There's no point in making a thing that's just got, you have some SPI and GPIO pins and everything else is hidden inside. I don't really want that. So the next level of integration is this, and Silicon Labs make a few of these kind of things. And this doesn't have a microcontroller on it, but it has, the interface to it is an SPI interface. So again, it's very integrated. And these things, these transceivers all have the same kind of stuff inside them. They have an oscillator, they have a frequency synthesizer. So this is a PLL to synthesize the carrier for the RF transmission. They have some kind of modem, and I'll talk about this in a minute. But if you're transmitting, the bit stream to be transmitted comes down here and goes here and goes through a power amplifier and goes out to the antenna. On the receive side, the signal comes from the antenna. There's a low noise amplifier, a couple of mixers, which are driven by the frequency synthesized by the synthesizer here, some filters, an amplifier chain, and this PGA stands for programmable gain amplifier. This is often a sequence of amplifier stages where you basically tap the signal from the first amplifier or the last amplifier stage that doesn't saturate, and this allows you to deal with signals of very widely varying intensities. There's a better picture of this in a minute. Then you turn your analog wiggles from the RF side into digital, and you demodulate them, and out they go to over SPI. This stuff in here is actually something I want to do in software, because this is quite interesting, I think. And there's a couple of interesting problems, particularly on the receive side. Transmit's not so complicated, but things like clock synchronization on the receiver side, it's kind of a fun little problem. So again, this kind of thing is a bit too integrated for me, because it has this stuff already done in hardware. And you can get lots of these things. So this is another one made by TI, and it's the same kind of deal. Basically everything in this box is stuff I'd like to do in software. And you see again, it's the same kind of pattern of RF bits. So I looked around for a while, and I found this thing, which is made by Maxim. And they've got another one, which I'm actually more likely to use. There's a 7032, which is the same kind of thing. But this is like a toolbox of transceiver bits, and I mean, this diagram, it might be difficult to see. There's lots of bits on it, and we'll come back to it in future videos. But if we look at some bits of it, it's got an oscillator, just like the other one. It's got a frequency synthesizer, which is a bit harder to see here, because so like on the transmit side, this loop is the transmit PLL. So you've got the usual phase detector, charge pump, filter, and a voltage controlled oscillator and a frequency divider. So that makes up the transmit phase lock loop. And then you've got a receive phase lock loop as well. So that's the synthesizer bit of this thing. On the transmit side, data comes in this way and goes through a power amplifier, goes out to the antenna. What's really interesting though is on the receive side, because you attach your antenna here, there's a low noise amplifier, but then the low noise amplifier output comes out as a pin, and the inputs to the mixer are as pins, and the output of the mixer is a pin on this thing. And you see the mixers are the standard kind of IQ kind of thing here. And then the input to the IF amplifiers are pins, and the output from the IF amplifiers are pins. And so all the different bits of the receive chain here are accessible to you to do things in between them. And this thing I mentioned about having a chain or a series of amplifiers is what you get here. And you basically, by looking at where you have the last one that saturates, you can tell something about the receive signal strength. And the other thing here, all this stuff down here is what people call the data filter or data splitter, which is sort of the heart of the demodulation part of things. And for this kind of on-off keying, basically what you do to demodulate stuff is you compare the values coming in from your receiver with some reference. And if the value coming in from the receiver is greater than the reference, you say it's a 1. If it's less, it's a 0. And so this comparator here is the heart of this bit of demodulation. And as ever with a comparator, the question is, how do you set this reference? And there are various bits and pieces you can use to do this, like some peak detectors here, where you can set a fixed reference if you know. You can feed the peak detectors from the output of the IF stage. So, I mean, there's various things you can do with this, and I like this level of de-integration because it gives you a good insight into how this stuff works in a relatively gentle way, because you can take the example circuit from the application note and more from the datasheet, more or less copy it, and have a fairly good chance of it working. So I'm going to do something like that. And the interface that this thing has, this one doesn't have an I2C, it just has some pins for setting some gain control stuff, but it has this transmit receive switch and enable pin and this bidirectional data pin. So I kind of like the way that this thing works. And the other part that's similar to this is there's a Maxim Max 7032 as well, which is the same as a 7030, but it has an I2C bus for some configuration stuff. So I like that kind of setup of a toolbox of RF parts. So there are only really two main components on this Link-434 board. One is the transceiver, and the other is a microcontroller, which will drive the transceiver. And to get some idea of how big and beefy a microcontroller is needed, you need to think a little bit about what the software needs to do. And this is a different kind of problem to the Minimapper board, where the Minimapper board to me feels much more like we're running application software. There's going to be some, like there might be a logo interpreter and a thing for driving around doing total graphics. There'll be some mapping software, things like that. The Link-434 is a much more embedded thing, because it's just got one job. It's always going to be doing the same thing. You will only be loading different code onto it if you find bugs in the firmware or you want to change the protocol that it talks. So let's look at a little cartoon of what this thing will have to do from a software perspective. So here's my little cartoon of what the firmware in the Link-434 is going to have to do, and I've drawn the interface to the transceiver based on this Maxim part. So you've got the bidirectional data line, and you've got a transmit receive signal, and that's basically all. So if we start at the left-hand end, we've got the serial interfaces, the USB and the UART interfaces that this thing can use, and so you'd connect a PC here, or you'd connect to the Minimapper board here, and they'd talk some protocol to this thing. And so the first thing you need to do is deal with that protocol. And it doesn't need to be very complicated. It'll have messages that say things like, your address is this, switch the radio on, send this message to this address, just simple stuff like that. Maybe ping this address. And on the way back, for received data, it'll turn the received data into messages that make sense to whatever's listening on the other end. Then let's talk about the transmit chain first, which is these orange boxes, because it's a little bit simpler. When you've got some data to send, the first thing you need to do is put it into a frame. And a frame is basically the lowest level binary representation of the data that you're going to send. So you'll have something like there might be some kind of preamble to start the data frame. You might have some frame type, so you might say this is an acknowledgement frame, this is a normal data frame, this is a ping, something like that. You'll have some kind of length to say how big the payload is. You'll have the payload, which is the data that comes from here. And then you'll have some error checking, so a cyclic redundancy check in this case. And so you take the data from your serial messages coming from the client, whether it's a PC or the Minimapper, and you put it into a format suitable for sending on the wire, although in this case there's no wire. Once you've done that, there's an additional encoding step that's needed for these kind of radio applications, and the idea here is to try and have about the same number of ones as zeros. So if you have a long sequence of zeros in your binary data, this can cause problems in terms of the detection at the other end, and because you can think about this, that this basically means the transmitter will switch off for the whole of this time, and that can make things like synchronization at the other end difficult, or just detecting that there's any signal at all. So what people do is they use this thing called Manchester encoding, or similar schemes, and what this does is it basically encodes bits as transitions, and so you end up with a bit stream that has a more or less equal number of zeros and ones in it, and lots of transitions, which makes it easier to send. And once you've got that bit stream, you have to shoot it out through a GPIO to drive the transmitter. And some microcontrollers have waveform generators in them that might be handy for doing this. So that's a thing to think about. And then you want to transmit this stuff, which means sending it to the transceiver over the data line. You also need to switch on the transmitter, but you want to make sure that you're not transmitting at the same time as someone else is transmitting. So you need to have some collision detection scheme where you sit and listen before sending, and there's some kind of timer stuff going on here that decides when it's okay to start trying to transmit. And that means that there needs to be some kind of queue in here to hold these messages while they're waiting to be transmitted. So that's the transmit side. It's not terribly complicated. The receive side is a bit more subtle. So most of the receive side in these blue boxes is the opposite to the transmit side. You capture the Manchester encoded waveform that's coming in, you decode it from the Manchester encoding to normal bits. You unmarshal the frames, so you check that the frame's the right length, you pull the payload data out of it, you check the CRC, and then you either send a data message back over the serial connection, or you send some kind of error message to say that the CRC failed, or I got something weird, or I don't know what's going on in whatever way. The complication that goes with receiving is that when you transmit here, you transmit some kind of bit stream, ones and zeros, and you transmit that at some clock rate that is based on a clock that you generate locally. When you're receiving, your clock rate doesn't necessarily correspond to the clock rate of the transmitting end. And so you need to do something about synchronizing your clocks. And the easiest way to do that is to stick a preamble on the front of the message that just goes 1 0 1 0 1 0 1 0 a bunch of times. And you can measure the times between the edges in this preamble, which is a shape that you know, and you can use that to determine how often you should sample the bits that are coming in afterwards to get the same sample rate as was used on the generating side, on the transmitting side. And so I think the scheme to do this shouldn't be super complicated, but it is an extra complication with the receive side. So this is what this thing needs to do, and it's, to my mind, it's not super complicated. And my temptation is actually to look for more or less the smallest microcontroller I can find that will do USB, because if I run out of compute headroom on this, I can just reduce the symbol rate. I can just send data at a lower rate, so I need to process it at a lower rate. I have complete control over this, so I have a lot of flexibility in how this goes. If I said I want to do, I don't know what's completely unreasonable. If I want to do 1 megabit per second over this thing, I would have to sit down and work out quite carefully the timing budgets for this and the how beefy a processor I need. But because I don't really care very much if I end up only getting like 1 kilobit per second, then I can be much more flexible. And I'm kind of tempted to pick a microcontroller that's fun and that I'll learn something new from. So let's have a look at a couple of microcontroller options anyway. So if you go looking for microcontrollers that have USB capability, starting at the biggest, there are some STM32 parts. There are some other manufacturers that make Cortex M0347 parts that have USB. But this feels like kind of overkill for this application. I don't really need a 32-bit processor with loads of memory and really fast to do this. There are lots of MSP430 parts that have USB. They're 16-bit. I don't know, I mean, they're an option, but there are also 8-bit processors with USB, which to me sounds kind of fun. I remember when I was a kid doing Zilog Z80 assembly programming and it being pretty entertaining. And so there are a bunch of PIC parts that have USB in them, but there's also these parts made by Silicon Labs, which are my current favorite option. They have this series of microcontrollers they call Universal B, and they're 8-bit microcontrollers with a C8051 core, a few peripherals, and a USB thing. And they look quite nice. And so I think I might have a go at one of those. And the C8051 is one of these kind of classic embedded microcontroller cores. And I've never used one. So, I mean, it's either that or a PIC, really. So the way to proceed with this seems fairly obvious. I need to pin down a choice of transceiver, which I'm getting close to doing. I need to reread some of the data sheets for these things, and I need to pin down a choice of microcontroller. And that seems relatively clear. I need to kind of stare at my cartoon of the software requirements and maybe draw some pictures of kind of buffer sizes and queue sizes and things just to get an idea of the amount of memory that's needed, and then pick a microcontroller, and then I can start doing schematic capture. And I mean, the next video or two will be about that stuff, and then I'll go back to the motor prototype board work. But see you next time.